Okay, gang, so this is the next installment of our modules, section 4.5. Next thing we're going to cover is optimization, and this is going to be another application of using the derivatives. So our first applications of seeing the derivative, remember, was rate of change, slope of a tangent line, also instantaneous rate of change or velocities, okay? Then we saw in chapter 4, the beginning of chapter 4, we could find maximums and minimums, increasing, decreasing, concave up and concave down, right? So there's quite a few applications of derivatives. Now this is going to be another one, optimization. And the idea is this: given some kind of a quantity, right? So maybe the profit of a company or the cost of a company or any kind of quantity. You want to determine the number of units that are going to maximize that quantity. So for example, maybe you're a business owner and you want to determine how many skateboards you have to produce in order to maximize your profit, or how many skateboards you have to produce in order to minimize your cost. Things like this. So real world situations, okay? It's not new math. Don't forget that. I know section 4.5, when you start looking at the exercises, you see all those word problems in there. It looks a little bit daunting, right? Always with the word problem. Just remember, keep your wits about you, gang. It's going to be maximizing and minimizing functions. How do you find maximums and minimums of functions? We find the domain for the function. We look for critical numbers. We do sign diagrams. All that stuff still applies, okay? Let me show you what I'm talking about. Here's an example, okay? Let's suppose that you have exactly 100 feet of fence, and you want to go out in your backyard and you want to make a rectangular garden. And you want to use all 100 feet of fence, because if there's any excess, you can't take it back to the hardware store, right? So, but here's the thing. You want to make it in such a way that then you're going to maximize the area. You want the largest rectangular plot possible with that 100 feet of fence. And one other stipulation. The house is going to be a border. Okay, so you only need 3 sides to the fence. So something like this. Okay. So this is the area that you want to maximize. Okay. So what are the dimensions that are going to make that happen, right? Well, in order to determine that, gang, remember, think about all the math that we've done. We're going to be looking for derivatives, critical numbers. We need an equation we can take the derivative of. We can come up with one for this. Make a note. You want to maximize area, okay? And I think it's important, gang, when you're working through these problems, whatever quantity you want to maximize or minimize, actually write it down, okay? This is what you want to maximize or minimize. Why? Because ultimately, that's the quantity you're going to find the derivative of and find critical numbers as well, okay? Now we need an equation for that expression. All right, well, we can get that from our figure. Let's do this. We're looking for the dimensions, right? Let's let this be x. And then by symmetry, this will be x as well, okay? So ask yourselves, gang, of the 100 feet of fence, how much did we just use? How much did we just use? Good, 2x. So how much is left to make the third side? Good, 100 minus 2x, okay? Now, what's the area of a rectangle? The length times the width. Okay. Now you've got a function you can work with whose derivative you can find, and therefore you can find critical numbers. Okay. Now let's put a domain on this as well, because gang, while this may be a polynomial, we know that the domain of all polynomials is all real numbers. In the context of this problem, you can't use them all. For example, you can't use negative numbers, right? You're talking about the dimensions of a rectangle here. Negative numbers are not going to do. So you're going to have to cut out everything up to the origin, all right, for the x's. On the other hand, you can't go out as far as you want either. You can't go x to infinity for your domain. That wouldn't really make any sense here either, right? If you go too far out in the domain, the length of the rectangle is going to wind up being a negative. For example, suppose you use 51. Okay, suppose x is equal to 51 and you plug 51 into this. You're going to have 100 minus 2 times 51. That's going to wind up being a negative number. So you can't go out as far as you want either. The domain that's going to work here is everything from 0 up to 50. Okay? Now, think about this. Remember back in section 4.1. 4.1 said, if you have a continuous function, and this is because it's a polynomial, on a closed interval, you're guaranteed that this function is going to reach a maximum, absolute maximum, and an absolute minimum. Okay? And it doesn't tell you where, of course. It could be at the endpoints, it could be in between the endpoints. That's up to us to figure out. But more to the point, gang, this is a section 4.1 problem now. Right? Once you take it out of the realm of word problems where everybody gets, there's a certain level of angst, right? But now we're looking at a 4.1 problem. Okay, let's go get the critical number. First, I'm going to simplify this. Okay, find its derivative. Okay, now you're looking for critical numbers. Remember, where are critical numbers? It's where the derivative is either 0 or undefined. This derivative is not undefined anywhere, so you're not going to get a critical number that way. The only other way to get a critical number, force that thing equal to 0. When does that happen? When x is equal to 25. Okay, now 25, that is in here. 25 is in here. All right, so again, using the procedure of section 4.1, now I'm going to take that critical number and I'm going to evaluate the original area function at both endpoints and the critical number in between. So it's a calculator problem now. Okay, so take all three of those numbers, gang, put them back into the original area function. You can use the factored form or you can use the expanded form. It makes no difference. We have scientific calculators. None of this is frightening to us, right? If you use this form right here, you can see right away that at 0 and at 50, both of these are going to wind up going to 0. At 25, plug back into this. You're going to get 1250. Obviously, gang, that's the largest number on the list. Right? And remember, the largest number on your list is your absolute maximum value. So the area under the context of what's going on here, 100 feet of fence, 3 sides only. The maximum area is going to be 1,250 square feet. What are the dimensions that are going to make that happen? We'll come back up here, right? X is 25. Find the length now. Plug 25 into this as well, right? 2 times 25 is 50. 100 minus 50 is equal to 50. So the dimensions of the rectangle that are going to maximize the area, 25 by 50. What is that maximum area? 1,250 square feet. Okay? So we'll do a couple more examples of this, gang, but essentially this is what it comes to. Remember this, though, as you work through these homework problems. Whatever quantity you want to maximize or minimize, write it down right away. Make a figure as well. The quantity that you want to maximize or minimize is going to be that equation, that expression, that quantity that you want to find the derivative of and then therefore find the critical numbers for. Okay? All right, we'll do another one.